CU Coventry, I've had the opportunity to go on placement next year and have a listen to network rail.
Alright everybody, hello, hello, hello. Hello, 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 hello. Can we all come back together? Can we all come back together? Can we all come back together? Hello everybody. Come on, hello everybody. Hello. Alright, good, the excitement is here. My name is Adolphus Duru, and I'd like to officially welcome you to the October Midlands LabVIEW User Group. Shall we all just sound excited? Yay! Alright, brilliant. I'd like to start off by welcoming you to CU Coventry, a member of the Coventry University Group. There will be lots of talks, there will be the opportunity to see the building and our fantastic facilities, but officially welcome to this event. Now, to officially start the event, I would like to call on our Head of Curriculum, Mr. Jon Melville, to give an introductory note about CU Coventry, how we teach, how we learn, and why we are massively paving the way for teaching and learning in the United Kingdom. So could you please join me and just give a round of applause to Jon Melville, please.
Right, can you hear me? Because I loathe microphones. which is going to be ironic in a moment. Welcome to CU Coventry, which is Coventry University's widening participation arm and our innovation arm. Widening participation is key. We're a low tariff, low cost institution. We take students with poorer results, potentially more vulnerable students, and we get phenomenal results out of them. We have, 67% of our students are first generation higher education in their family. We have approximately 70% Black, Asian, minority ethnic male students who are generally regarded nationally as least likely to succeed of all the socio-economic ethnic groups. We have an 87% achievement rate of students walking out of here with a degree, and 81% of those who walk out, 70% of our starters, walk out with good honours. Now, you don't get that without innovation. We have an innovative curriculum model. 6 start points during the year. The students do 4 standalone modules in the year. Each module stands alone, you start, you finish, and you get the results about the time you start the next one. So you know your progress, you know where you're going the whole time. You've only got one live assessment, you've only got one thing to worry about, and with multiple start points, you can step out if you need to and step back in. So those vulnerable students who might have family issues, personal issues, well-being issues, financial issues, they can step out and back into the curriculum without failure or without having to repeat an entire year. We have that flexibility. We've also innovated in the way we deliver curriculum. It's not about lectures. In fact, they don't happen. Most of the delivery, if there is delivery, is online YouTube recordings. Yeah? Talk to the tutors around about how they're delivering that. A lot of the stuff is a bit of YouTube film, a little thing to read, and some exercises to do before the following day's class, which is active and practical. The learning environment doesn't have screens, whiteboards, projectors, or a lecture, which is why I don't like talking into microphones, because I don't stand still. Okay? The learning environment has a Bluetooth headset and a tablet for the tutor, and the student has a screen in front of them, a PC in front of them, and a headset they're wired into with throat mic. So you're in one-to-one communication with your tutor. Whatever they do on their screen appears on yours. That means not only do you have a much closer, more personal relationship with that tutor, even though you're in a large group, but we can record all of that. So, firstly, if you need to review something because you didn't quite get it first time, you can go back and rewatch it. Secondly, if you missed the bus, you can participate in the same session remotely from home. And thirdly, if you overslept, you can at least witness the session later on in the day. All of those contribute to building the flexibility, building the support for our students. In addition, we've moved away from knowledge. Knowledge is of declining value. I keep saying that. I've been saying that in meetings and conferences quite a lot recently, and people go, what? We suffer the danger of teaching students something in their first year that is already obsolete by the time they graduate. So don't focus on knowledge, focus on the skills so students can acquire knowledge for themselves. So we build that in the first year, we apply that in the second year, and the third year is pure project-based learning. No whole class teaching. The students build the skills so they can find knowledge for themselves. So that rather than being dependent on a tutor to tell them what they need to know, to tell them what they need to do, they go and find it out for themselves. And that way, when they land in the workplace, they're expert at that already, and not having received a formula for failure by being dependent on a guru. What happens is scary for the tutors, because the tutors come back at you. The students come back at you with questions you weren't expecting, because they've found the knowledge from other places, and it's not where you directed them to, it's where they found it. And they come back with left field questions, which is great. It can be scary, but it's great, because it gives you an opportunity to actually let those students realise that I'm not the real expert here, I don't know everything, and let's find out the answer to that together, and they work on collaborative learning with you. This whole thing was designed with the needs of industry in mind. The main lab is pretty much a replication of an R&D lab in several companies. It's not a teaching environment, it's a working environment, and our final year students are effectively working like employees. They're working on projects continuously through the year. They're industry ready when they leave us, because when we designed this facility, when we designed this course, we went out to industry and said, what are your problems with raw graduates? And they came back to us with, they're too dependent on the tutors. They don't have the capacity for independent thought and going off and managing their own learning. So we turn that on its head. So far, very highly successful, which is a real credit to the teaching team here, because before March, they were in a standardised, boring classroom environment, a box that needs a lick of paint, tables that all face one way, and a whiteboard and a screen at the front. I'm going to deliver to a bunch of students who are expecting to be passive. And in March, we flipped the whole of that and put them into a whole new environment. And the teaching has been phenomenal. The staff have been absolutely brilliant at not just going, I've got to change, but embracing that change and going, how can I take advantage of this, make advantage of this, and improve the experience for the students and for myself. Okay, that's pretty much me. Any questions? I think Adolphus has me down for doing all the guided tours during the afternoon, so you'll have an opportunity to ask those then. Thank you.
Right, just a quick welcome from me. My name is Chris Woodhams. I'm Managing Director at Argenta, who run the user group. It's great to see so many faces, it's wicked. I hope you guys will come along to other user groups elsewhere. Just a quick overview of the agenda. First of all, we've got one of the students from CUC coming along to talk about a project they've worked on using LabVIEW. And then we've got James McNally, who's going to talk about LabVIEW OOP, which is object-oriented programming in LabVIEW. And then we've got a little break, and then we're going to talk about the coding challenge. We've had a couple of responses to that, so I'll walk through that. And then I finish off with a little bit of a discussion about how we successfully complete projects. And that's not we as in me, that's in us. So we're trying to learn for everybody else. So yeah, without further ado, well, after these guys have set their laptop up, they'll be jumping into the presentation.
Thank you. Alright guys, sorry. One of the things that we're really proud about here at CU Coventry are our graduates. We believe this is like no offense, this is like a workshop or like a factory, and our graduates are our final product. So one of the things that we've done today is, as a department, we're here to showcase how our teaching and learning has helped support one of our students who is currently doing his final year project. And he'll be talking you through how he started his LabVIEW journey with absolutely no knowledge of LabVIEW, and how within 6 weeks of learning and teaching, he's gone from that literally minute knowledge to where he is today. He's not there yet, but the journey has begun, and I'm very proud of Bob and excited about what his future holds. So without much ado, I will let Bob Kelvin have the stage. But I understand that in the room today there are lots of really professional coders. I'll ask you to tamper mercy and not to be too critical of his code, but to appreciate his journey, okay? All right then, thank you ever so much. It's all yours, Bob.
My name is Bob Kelvin Patrick. I'm a student of CU Coventry, and today I'll be presenting my Mechatronics project on temperature measurement system. Mechatronics has evolved in recent years, which has led to smart new products. A temperature measurement system is an important measurement parameter in the industry today because of its wide application. Every aspect of life has a relationship with temperature, from having a thermostat in your car to it being used in industries. To measure temperature correctly, different sensors and devices are employed. A circuit was built and designed in 3D and printed up at the engineering lab, and this was possible through one of the pillars of Industry 4.0, which is 3D modeling and printing. A thermistor, the chosen temperature sensor for this project, combines two or more metals to give a negative temperature coefficient, which provides a principle that governs this operation. A thermistor's electrical resistance has a relationship with temperature. That is, it's inversely proportional to temperature. So when one increases, the other decreases. And this can be expressed using two mathematical equations. The first one, the Steinhardt formula, and the beta equation. Both equations were used for this project, and the thermistor's resistance was measured using a voltage divider. My hardware configuration. I used a 10K ohm resistor, Mario, a thermistor, LED, breadboard, and that's my circuit diagram. I'll be explaining a bit of the code. The thermistor's resistance has more than one analog input. So an analog input express VI was chosen to read the resistance using pin 3 and 5 from port B. The values were then fed to a calculator programmed to be a voltage divider. A case structure was chosen to house both equations as a subdiagram or a case, which allowed both programs to execute whenever you switch between them. An indicator was also created to display the temperature in degrees Celsius. I went further to program 3 LEDs to stand as an indicator. The red LED indicates high temperature, the yellow room temperature, and the green low temperature. This was programmed into the sub-VI2. while the SubVI one was programmed to display temperature in 6 different temperature SI units, like Fahrenheit, Kelvin, Newton, and a host of others. The whole code was fitted in a while loop to allow the code to keep running until stopped by the user. Now I'm going to show a demonstration on how my device works. As you can see right now, one second. Okay. So as you can see from the screen, this is my interface, my front panel. You can see the temperature reading right now of the room in Celsius. You can see it using Steinhardt formula, and you can see it using beta formula. Right there, if you look at the indicator on the left, you can see that the beta formula is the one in use right now. You see the SI unit of the temperature, current temperature of the room in different other SI units. So I'm going to test it right now. I've got hot water here, and I'm going to put on the temperature on the thermistor, and you can see it increasing.
What's the threshold?
31 degrees.
And guys, can we check the temperature up to get there? Let's be excited. Let's share it up. Share it up. Come on. Yay! So we're there now.
And on the device, the red LED is on.
Yeah, you didn't let us check. Right, go on.
All right.
Thank you.
I'm also going to, I've got ice here.
What's the pressure?
Below 16 degrees. Now this is the room temperature, and we're going below.
Come on, again, come on guys, come on. Yay!
And the LED, the green LED is turned on.
Thank you. How is this connected? Over
Wireless.
Bro. I know, right?
I was introduced to LabVIEW in March while I was doing my robotics module. Within 6 weeks of learning, I was able to program a line-following robot with the ability to clear obstacles in its path. I hope that this actually created a foundation for my current project, which I did, and the one I'm doing for my finals. I hope with time I'll be able to learn more functions of LabVIEW, like use functions like queues for memory efficiency. Thank you for listening.
Do we have any questions for Bob? No. No questions? He came prepared. Come on, guys. No, Bob is very prepared. I think one of the things I appreciate. Oh, hold on, not you. One of the things I appreciate about this gentleman is he had never heard about LabVIEW at all until his 3rd year when he did the robotics module. Yeah. And then from zero knowledge, he has been able to leap to where he is. I mean, he's connected the system over Wi-Fi, and he's done exceptionally well. And I'm very proud about him. I'm proud about his journey because he has gone on to take LabVIEW for his final year project. And he's doing something very interesting. I won't let the cat out of the bag, but hopefully at the next Midlands LabVIEW User Group, hopefully, when he has himself published and all, we could showcase him again. But he's done very well, and we're very proud of him. So, guys, we'll have some questions. Some easy questions.
What was the easiest bit and the hardest bit about picking up LabVIEW?
I'll say the easiest bit is because it's a graphical program, so it's easier than writing text-based, writing your code in a text-based program. So that's the easiest part. The hardest part was when I saw my assignment brief and I was like, how am I going to achieve this in 6 weeks? But with the help of my tutors, the lab attendants and everyone, this was possible. Yeah.
Slightly off topic, can you tell us more about the case? You mentioned the case, can you tell us more about that?
So that was designed with Paramedic. I took my measurement and everything, I designed it on Paramedic, and we printed it through a 3D printer available up in the engineering lab. What I did was that I created a plan. I had a sketch and I went with my sketch. Do you have any more questions?
And now you're showing up. Alia?
Yeah, sorry, I'm way back here. So in LabVIEW, you said that you have a case structure. How many cases do you have and what do they represent?
I have 2 cases in my case structure. I'm just going to show you. So the first one is the Stein hat. I've stopped it. And the second is the beta, for the beta equation.
All right. Any more questions? So I'm going to stand as Bob's agent today. So in case you are looking to recruit him or sign him up, just pay me my agency fee and all, and then he'll be all yours. But let's put our hands together for Bob.
Thanks very much, Bob. I really appreciate that. It's very brave of you to show your code in front of so many people. So we're a friendly bunch, though, so we will. Right, next up, James is going to give us a presentation on LabVIEW OOP. So whilst he gets set up, I will tell you a joke. No, I don't know any jokes. Yeah, I'll leave it to James. Yeah. Let's see if it's
went through it. I dumped my bag on the way in and then didn't see it anywhere next to it, so I haven't just started it up yet.
So just a quick show of hands. Who's using LabVIEW at the moment in their course or work world? Pretty much everybody? But everybody knows about LabVIEW, or everyone knows about LabVIEW? Yeah? You will do after the end of this, hopefully. It's good to see that the guys from Argenta are putting their hands up as well.
So apologies for my poor preparation, it will come up in a second. What I will say is I can sort of keep this high, or I can dive in a little bit more depending on what you find interesting, so please do, I'll try and look out for hands, please do stop me, ask questions, and we can kind of keep this pretty flexible depending on what you guys find interesting. Let's get that ready to go. Perfect. So my name is James McNally. I'm from Wiresmith Technology. So today I wanted to talk a little bit about how to learn OOP, and I'm going to throw a load of caveats at you as we go about what I mean by that. But I guess the whole point of this presentation is that object-oriented programming is a huge field, and there is great complexity in places. My personal belief is that carries too much baggage, and actually there's some simple stuff you can do in LabVIEW to start learning it, to start working with it. And you don't ever need to get to that complex stuff without getting a lot of benefit. So this is kind of from a blog post I wrote a little while ago, trying to take you through, rather than here's the manual, think about the steps to go through to kind of develop your understanding. So, actually, I should probably start. How many people have heard of object-oriented programming? Maybe half the room. So, the basic idea behind object-oriented programming is that rather than the kind of traditional programming paradigm where you would have had, here's a bunch of data and here's a bunch of functions, you combine the two and describe the world in these objects, where each object has some data associated with it and some functions that perform on that data. To give a really classic example, which doesn't really help very much in reality, but a car object might have an engine, a steering wheel as its kind of its parts, and it would have methods, things it can do like drive, turn left, turn right, as an example. So that's the idea. It's supposed to sit more naturally with how we as programmers view the world. As humans, we tend to look at things, we'll look at a chair and we'll call it a chair and we'll say this is what it can do, it's black, it's made of metal. And that's the concept behind it. So that's one of the reasons to learn it. The whole idea is it's supposed to, a software program is very often a model of something. It's a model of the world around us. We're kind of representing what's happening in the real world so that we can manipulate it in some way. And so it fits a little bit closer with that. My first caveat of the day. 4 very data-centric processes. There's another class of programming called functional programming, which for certain problems is certainly better than object-oriented. And the reason I mention that is if you search for it, there's a slight tug of war going on between the two in the wider world at the minute. The big thing for me is what it helps to do is abstract away some of the details. So I'm going to talk a lot as I go through this about kind of details and abstractions. And what I really mean is the details are like the implementation details. We're talking to something over a serial protocol, or the way that we're doing this particular algorithm is an FFT or a DFT or the various formats. And what OOP can kind of help you do is hide that a little bit and talk in the problem domain. So rather than talking about a serial protocol, we can talk about a pressure meter. Rather than talking about an input voltage, we can talk about a temperature measurement as we saw before. And even if none of that sounds interesting, for me, it's just a really nice way to organize your code, to structure your project in such a way. The real goal is we say, there's a problem with this bit of code, I know exactly where I need to go and find that. So I kind of mentioned some criticisms, and I wanted to talk about those up front as well, because I think that's important. As engineers, we're making decisions, we're not following a true path. So things that can go wrong with object-oriented programming is you get unnecessary abstraction. So you might end up with so many layers of abstraction that you don't really know what's going on anymore. And that's definitely a risk. Another one I've got, design patterns gone wild, and I'm going to put up an example of this. So at the more advanced end of object-oriented programming, there's this idea called design patterns. And what has happened, and depending on if you're being critical or generous to them, it depends on where the blame lies, is people see these design patterns are brilliant, I'm going to use them everywhere. And you end up with names like it's a temperature factory controller, and it stops, again, it's kind of related to the first one, it stops making sense to the problem you're actually solving. So I'm hoping through this, I'm going to try and help you avoid this by finding some baby steps rather than jumping in at the end, finding some steps to go through to help some fundamental understandings which may help you avoid these traps. The last one that's worth mentioning is specific to LabVIEW is the performance of LabVIEW itself. So historically there are plenty of examples where someone posts on the forums, I've got a project with 300 objects in it and it stopped working. I still can't tell you a definitive answer about this. What I can tell you is I've never had that problem. And I think there's objects and there's also some dependency issues that contribute, and I think there's a number of elements that contribute to that. So that in its own right, I don't think is a reason to not worry about it, but it can happen if you get a bit too crazed with them. So, like I said, the big point of this is we're going to chuck our design patterns book in the bin. We're not going to go and read everything we possibly can. We're going to start small. We're going to take some steps towards trying to understand the fundamentals of why object-oriented programming, which will help then, when you get to these more advanced topics, understand when and where to use them. I'm not going to throw out all the computer science. That's what some people would like to do. I have found one of the computer science terminologies around this very valuable. I don't necessarily think it's the clearest, but it's a good framework, so I'm going to take you through these. So these are called the solid principles. They were from a book by Uncle Bob Martin, but they have come from other places before. He just put them all in one place for the first time. And so if you speak to a lot of object-oriented programmers, they're going to know what you mean by solid principles. Hopefully this process is going to mean you understand them fairly well by the end of it too. So I'm not going to go into the details now, we'll go into them as we go through. But there's a secret behind all of this that if any of you know Steve Watts, you'd be quite pleased with, is all of these principles all come back down to a fundamental principle called coupling and cohesion. How many of you have heard of coupling and cohesion in terms of programming? Just one or two. So, coupling and cohesion are concepts that are designed to keep your program very modular, and the reason you want to do that is it tends to keep code that's easier to maintain, easier to change. These aren't an object-oriented term, these have been terms coined long before object-oriented programming existed. So coupling is about how interconnected things are. So if I have a couple of software modules and they're all dependent on 50 others, that's a very highly coupled system. If I have a software module that doesn't depend on anything else, it's a very low coupled system, but it's probably useless. In reality, there's a number between those two that's an ideal number, and the lower that number is, the better. And cohesion is, with those software modules, how well defined is it that, well defined is the wrong term. You want everything in that module to be working to a single task or a single responsibility. So if you have a software module that's responsible for acquiring your data and logging it and putting it on the user interface and sticking it in a database, that's a not very cohesive module because it's doing a lot of different things. If you have one module for data acquisition, one module for writing to a database, one module for, what else did I say, logging to a file, then that's more cohesive because each module has a single purpose. And that's really the end goal of all of this. It's to have well-defined modules with low coupling and high cohesion. And the way of object-oriented programming I'm going to show you is really all tailored just to getting to that level. So any questions on it before we jump into it a bit more? So, step one of your learning journey is the technical bit. It's the how do we actually make classes. So I am going to quickly fire into LabVIEW here somewhere. I've lost it. There we go. Ooh. Let's figure out what's going on there. So I appreciate you're probably not going to be able to see the detail. To be frank, the detail is all available online in the LabVIEW help. Oh no, not extend, duplicate. Let's see if that's still there. And actually quite nicely in line with what we've heard today. What I want to do today is not teach you all the technical details. It's a process to go through to learn this. But as many of you may have never seen what it looks like in LabVIEW before, I want you to be able to see that a little bit. So this is as far as I got with the coding challenge, unfortunately. I was going to have a bit more of a go at it, and then calls come in, and but this will give you an idea that, yeah, so I appreciate this is a little bit small, and this is where I need someone like James Powell who knows all the shortcuts to zoom in. I don't know if you can see, this is my LabVIEW project, and within my LabVIEW project, I have a cube. So everything in LabVIEW is that's an object-oriented thing is represented by a cube. So this is my, what we call a class. And so in this case, it's the score of a match. So within the score of a match, it has some data associated with that, which right now is, for the home team and the away team, a cluster with tries, conversions, penalties, drop goals. So you can possibly see with this as well, this is a cluster itself. Clusters and classes are very, very similar. The only difference is a cluster kind of exists on its own, whereas a class also exists with some VIs that actually manipulate that data. So for example here, I then have a read scores function, which is going to read out those two clusters and calculate the actual scores of the individual teams. And so the way I created that is in my project, I create a new class, give it a name. It automatically creates an empty cluster for me, so this is where I'm going to put the data associated with that. And then I can just create new VIs underneath that are the methods then for accessing that data. So like I say, I'm not expecting you to now be able to go away and do this necessarily. I just want to give a little bit of context to what we're looking at. There's so many guides for this online, you know, that you can go away and figure that bit out. In terms of working with them, so I've got some tests here. They're very similar. So basically, those methods that I mentioned, these are just sub-VIs. So it's very similar to what you're used to working with. And my score here, this is a constant for a LabVIEW class, LabVIEW object. So this is just represented as a cube. If I converted this to a cluster, it would be functionally almost identical. It's very, very similar to the idea of just having a cluster and VIs. We have an object and what we'd call methods, which are just VIs. The big difference is whereas a cluster, I could change the data on this wire by using bundle or unbundle in the middle. On a... Oh, what are you thinking about? Oh, there we go. That's not what I wanted anyway. If I try to look at the data in this class, LabVIEW breaks the wire. And that is the first really important concept behind object-oriented programming versus just using clusters and VIs, is what's inside this is hidden from whatever's calling it. It's a concept called encapsulation, and that's kind of the bedrock of our abstraction. So if I wanted to completely change, so I have those two clusters keeping the score, so that then I can calculate the score at the end. If I wanted to change that and I just wanted to have a single number for each one and add it in, this code would look identical. And that's the important point, is the details are hidden away inside the object itself. Any questions around that? So that's it. There's another big technical detail we'll come to in a minute, but you don't even need to worry about that yet. Just start there. It's like a cluster and VIs, but they're just logically grouped, and we hide the details inside. That's the really important concept. Again, it's our coupling and cohesion. Where it comes back to that is I can't start manipulating that data, I can't start coupling that data other than through its methods. So once you know how to do that, practice. I'm afraid I'm a big believer with, frankly, most things, but especially development. There are elements where the answer isn't in a book. You've got to go away, you've got to try things, you've got to muck a few things up and give it a go. So once you know how to build a class, you have everything you know to start being dangerous with them. So you're going to go away and do some practice, but this is where the solid principles come in. We're going to focus on two of them at this stage. The first one is the single responsibility principle. So that says every class should have one, the official wording is it should have only one reason to change, but actually that's a bit too vague in reality, and I'll show you some examples in a minute which will make that make sense hopefully. Essentially this is just cohesion, make it cohesive. Each class should do one thing and one thing only. The second one is called the interface segregation principle, and what this basically means is that class, the methods that are part of that become its interface. That's how you talk to the data inside that class. And so you ideally shouldn't design your classes so that if something's calling it only needs like half of those methods, then really there's two different interfaces there and they should be separate classes. I'll show you an example of that in a second. So this is a way of representing a class which is kind of like something called UML. UML is a kind of standard notation for representing classes. I didn't put a slide on it, but actually I was thinking on my way here I should have done. It's worth learning this a little bit, and this is a really simplified version. Again, you don't have to be experts in it, but it gives you a way of looking at the relationships between the classes, which can become important as we go through this. So this is a class for a pressure meter. The representation here is this is the name of the class, this is the data in the class, and then these are the methods for the class. So our pressure meter, we're going to talk to it over serial, perhaps, so we're going to have a visa reference here. We're going to have an alarm on this. We have an alarm level. If the pressure rises above this level, we're going to have an alarm. And so we have three methods. Read the pressure, evaluate the alarm, and then read the alarm message. So, how many responsibilities can we see? I'm probably already giving away that it's more than one. Yeah, so you can do 2 or 3 here, definitely. I've actually stuck with 2, but there's a lot of this is design decisions, and it's going to depend on how you're calling it as well. And that's another really important thing. These are design problems. They're not, like I said, they're not this is a right and a wrong. This is a design decision based normally on the call and code. So I've only split it to 2 because I think the third one could depend on how the rest of the design works. So the problem here is there's definitely 2 major things that will change this. So this is where you have one reason to change the class. If we change the pressure meter, maybe it comes over Ethernet instead of VESA, then we're going to have to change this class. Or if we change how we evaluate the alarms, we're also going to have to change this class. A really good clue here is when you start looking at a class definition like this, and there's multiple nouns, multiple things that seem to repeat a lot. So in this case, we've got pressure, but we've also got alarm a lot. So my first natural step with this would be to take that step to split it into 2. And we have a meter and we have an alarm. And as you say, there's definitely a case for the messaging part. I'm assuming this is where you're going with 3. There's also possibly a case for a third here, which is a message. This is obviously quite a contrived example, but at first you may find cases like this anyway. I had a very experienced developer send me a class definition asking for my opinion on design, and it was there in plain text. I was trying to find the details last night and I couldn't find them again, but there was lots of ands and obviously 2 different nouns that were spread within this. So this is the idea, and this is the first step in learning object-oriented programming. It's understanding how to break these down into small enough components that are still useful, but having them separate enough that you get the benefits of that cohesion. And again, the real benefit here now is if we change pressure meter, I can ignore all of this code. I don't have to touch any of this, I don't have to revalidate it. I can just look at this pressure meter and work within this class itself. as an example, as I was thinking through the rugby challenge. So I thought, well, maybe we have a match. So we'd have a home team and away team, and we'd have the different scores, and we'd be able to play it and read out the result. What could be some warning signs, I guess, on this, that maybe we're breaching the single responsibility?
Team and schools together.
Yeah, I think that's the big thing. So I guess my first alarm bell is just generally that it's big. We try and keep objects to having like a maximum of 10. Have you all heard of is it 7 plus or minus 2 things we're supposed to be able to keep in our working memory at a time? Use that as a guideline. So this has got 8 items now. There's kind of a lot of repetition in here as well, which it kind of feels like there's something else to go in there. So that's kind of what I looked at when I was thinking about this. There's also possible, and this is where I'll try and introduce that interface segregation principle a little bit. There's probably the bits of our code that are going to have the match played and that are going to be interested in the result are probably going to be quite different pieces of code. So probably have something completely different to display and work with the results than to simulate out the match. So possibly there's an interface segregation problem as well. But this is one of those cases where we don't really know just from this. We'd have to look at the broader application to understand if that's the case. But exactly that, I've split this out into 2. I kind of gave the game away on this earlier as well. And in fact, you can see, actually, when I came to write it, I evolved the design a bit more as well, and I put all these scores into 2 clusters within there. So it's very much, this isn't a you sit down and do it right first time process. There's very much a process that will evolve. And you can see, I'm still not sure, do we need the team definitions in there as well, perhaps? And then the match becomes the home team, the away team, and the result. So we've abstracted this away. So when we're working within the kind of context of the match itself, we probably didn't need to see all of these details. We only really need to know who's winning, who's losing.
Jim, in that then, the result element of your match is actually related to that class, right?
Yes, so this result element would be a copy, one of these would be stored within match.
They're coupled.
Yeah, so if I'd actually done, I should have just turned it to a proper ML diagram. You would mark a relationship between these 2 here to say that they're coupled together. A more obvious interface issue now is something we've probably all come across is DAT cards. So a National Instruments DAT card can do both input and output. So if you are mapping something straight to the hardware, you might have a single class that can do input and output. But I'd say 9 times out of 10, you need one or you need the other. So you would actually probably make 2 different classes, one for input and one for output. Because if you're doing an output, you probably don't need an input. And frankly, the overhead of having a separate input task next to it wouldn't be a big problem. As I say, all of these are very dependent on the context that you use them in as well. So that's also important. But hopefully, it gives you a few ideas around those 2 principles.
So if you had like a PID control module, this kind of would quite work, but you could probably do something around that approach to manage that, right?
Yeah, so a perfect example where you might want this is a control loop. And then this is where you have to start thinking about the design from what's useful to you. So probably actually in a control loop, actually it would be technically the same, you'd just name it differently. I would call this the system interface. And then however I decided to do it inside that interface, you could do it as one then, or you could call these 2 from within the system interface. That then becomes into the details of the way you want to think about it, really.
So the module could interact with those 2 classes that you've got, or you could have it as a single class.
Yeah, exactly, yeah. And without trying to scare things too much either, abstractions help us with readability, and they help us with the design. But the flip side is they can have performance and technical implications. So in that exact case, if the input and output could run quite independently, then I would be tempted to have a system interface class which calls these two. But you might have cases where they can't run independently. They both need to talk to the same hardware. You can't have two separate references to the same piece of hardware, perhaps because of the way the driver works. So then you'd have to have this. You'd be forced to this by the hardware. So there's sometimes there's different forces at play when you're trying to come up with these designs. Does that make sense?
Yeah.
It's always a trade-off, and actually, the trade-off is almost always, it does seem to be performance at one end and kind of abstraction or readability at the other. And so, generally, I'll start with abstraction, and then I'll break things down as performance requires it, depending on what you're working on. Cool.
So, James, this may be a bit of a tough question, but with Bob's example that he shared, how would you have set your classes up for that example? I appreciate you didn't see much of the code there, but you get an idea for what he was trying to do.
Yeah.
Is there sort of some ideas around how you would approach that with classes?
So the natural way I'd look is you kind of, one of the ways that you would often start to think about these is you look at they call it like noun parsing. So if you were to describe the problem in plain English, you would try and pick out the nouns out of that, and often they're a good starting point. So in Bob's example, the first obvious one is you have a temperature measurement. So I would call that what would I call that? Let's call it temperature measurement for now. So I would hide away a little bit. I would hide away the detail that it's actually an analog input from the main bit of the program. I would call it temperature measurement and have that generate a measurement in degrees C. So his cases for the different algorithms, the different ways of calculating that temperature would sit within that. Because at the top level, it's not a concern how that's done. We just want to see a temperature. And then when you are worried about that, you dive into it. It's not that you don't care. It's that at the top level, you're not too worried, and then you kind of dig into the detail that you're interested in. So then I think you could split it a couple of ways. My temptation would be to have it kind of depends. It's one of those things. It's how much do you add complication from our head that you think how would it scale? What would you do differently? I think I would make an LED displayer class, and I would make the user interface. You don't really need a class in LabVIEW normally. So then within that LED display class, you could just pass it the temperature, and within there it would decide which LEDs to light. So again, from your top level diagram, what you're actually looking at is temperature measurement, LED display, front panel display. So from a conceptual point of view at the top level, that's all you kind of really need to know, and you can understand how the data passes. Then if you want to understand how the LED display works, or you want to change it, you dig into the LED display and have a look. Oh, okay, so the LED display is turning on the red light above 26 degrees, or whatever the number was that Bob had set up there. And so that's the kind of idea, is you go up and down a little bit, but hopefully in ways that are useful to the way your brain's working, if that makes sense. I appreciate it's hard to follow probably me just talking through it. Are there any questions about that? It's quite a nice example actually. Yeah, cool. So, step 2 is we've gone away, we've practiced, and hopefully we're starting to get a good feel for these different, those principles. They're kind of really based on the coupling and cohesion, the S and the I of the solid. So this is the point, and I would suggest there's probably a couple of months in this at least, depending on how much you're coding and what you're doing. This is the point where we're going to learn about inheritance. So inheritance is a particular feature of object-oriented programming which is quite unique. It's normally what people want object-oriented programming for, and it's normally where people get in a mess. So that's the reason why I kind of push it back to this point, because it's easy to get carried away with what this can do, because it's technically kind of more interesting. But actually, it isn't much of the benefit. And this is something I very rarely use. You know, if I've got, so throw a number out there, 50 classes in a project, maybe 5 to 10 of them will be part of an inheritance hierarchy. So it's not the main point, but it can seem like that when you start. So that's kind of why I push it back to here. So the basic idea of inheritance is that you have, so if the case where we have the match and the score is what we'd call a composition relationship, or it's a has a. So a match has a score, or uses a score. Inheritance relationship you would describe as is a relationship. Actually, I won't, by the time I've got it in code, we'll have gone through it. So what I mean by that is the really classic example, again, which is useless to no one, but it inherits the point, is you would have an animal class, and you might have a dog class and a cat class. So a dog is an animal, a cat is an animal. And so you set up an inheritance relationship between them in the software and what that allows you to do is, so both animals can make a noise. So your code can just say animal make a noise. And it doesn't care whether it's a cat or a dog, it hides that detail away. So that's the idea. Finding real world scenarios where that works is more complicated. And honestly, again, this is where I really want to emphasize, it's about what's useful in your design. There aren't general rules to this. The classic example of this in LabVIEW is a hardware abstraction. So you'll say, I have a National Instruments DMM, and I have an Agilent DMM, and you create an abstraction layer, a parent in the inheritance structure, which is just a DMM, so you can use either of them. That's only really relevant if what you want is a DMM. If what you want is a voltage measurement, then that's bad. Because what if you want to use a MyRio? So that isn't a DMM, that's a voltage measuring device. So this is where things get a little bit more tricky and a little bit more complicated. So this is why I say, don't worry about this at first. I'm going to whiz through the next bits a little bit more in terms of the technical because, as I say, this is come back, learn the first bit, and start playing with this a bit more. So at this point, again, learn the concept, go away and practice. Spend some time, start using little bits of inheritance where it's useful to you. This is where we introduce the L of solid, which is called the Liskov substitution principle. And what that says is that if you have an inheritance structure, all of the children, all of the specific types, must fully support what the abstract type is. So a dog and a cat perhaps could work, it depends on what you need. Actually, no, I'm going to ignore the dog and the cat, let's talk about another one. The classic example for this is shapes. So there's a case where you can say a square is a rectangle. It's just a rectangle with a very special condition where the width and the height are the same. Now that works, but what happens is when you set the width on a rectangle, you can set the width and the height separately. Whereas on a square, what has to happen is when you set the width, the height has to change. So you're kind of breaking some of the relationship there of what you expect to happen. So you could say that fails the substitution principle because they're doing different things. They're acting in different ways when you treat them as a generic type. Another way that they kind of talk about this is called leaky abstractions. Technically, you've tried to abstract away a square and made it a rectangle, but really, you need to understand that sometimes it acts differently. And some of that abstraction kind of, what's the right phrase? Leaks through, that's what they call this. You need some detail about what's going on to understand what's going on. There's a few famous quotes, and I forget the witty ones, but essentially all abstractions will leak a little bit, probably. The idea of perfectly adhering to this is very, very difficult in real life. What you don't want to do is get to a point where it's completely useless, and you're having to check what type it is before you do anything with it. So again, the books will tell you one thing, the real world will tell you another. So this is again why I say, take this concept, take this new concept of inheritance and just play with it a bit, try it out, find cases for it, and sometimes it'll break. And you'll start to get a feel for that.
We had quite a good example with inheritance, bringing it back a little bit, where we had a common, like RS232 comms class, and then we could create child classes for those for each device. And then, so we would have a child class for a screwdriver, which is communicating over RS232. So you still need to do all the initialize, and all the readings the same, like setting the baud rate. You might have those that you'd override in your child classes, but then it doesn't matter because so it doesn't matter whether it's a screwdriver, whether it's talking to a PLC, whether it's talking to something else. It's all sort of using the same class and then overriding what we need. That was quite neat.
Yeah. But if the interface,
yeah.
An example of where an example of how that might leak, and this isn't to criticise it, this is, like I say, some of the real world things that will happen, is suddenly your screwdriver needs a second to initialise, and your PLC needs 30 seconds to initialise. And you start going, okay, well, when we do the initialise, we need to add a timeout, and we need to know which one we're initialising. So that's an example of, from my point of view, a perfectly acceptable leak. Well, if you could do it without it, even better. But that's a great example. Devices are a really good example in our world for this kind of abstraction concept, as you can treat them very much the same. I had a similar one testing freezers. So I had a freezer class, and underneath that we had a Modbus-based freezer, a serial-based freezer, a serial one with a different protocol, and that's an interesting one, because the serial ones had to have a start function, and the Modbus ones didn't. So the start function was just empty for the Modbus ones, and in that case, again, it kind of doesn't leak too much because we do all the same thing. But there's some upward pressure from the devices on what that becomes. So it's hard to idealize a lot of these things in the real world. How am I doing for time? I've lost track of. Right. So once you've done all of that, and I'm talking 6 months down the road here, and that's an important point. And maybe it'll be faster for you, maybe you've got some more background. This was my personal experience, was I started trying to learn everything at once, it didn't work. I came back and kind of went through this process. Now we can start to look at the final two concepts, which are called the open and closed principle, dependency inversion principle. Again, I'm not going to cover those in detail now. You can come and ask me about them later if you're at this point already. And then get your design patterns book out of the bin. And then start looking at them. Because the interesting thing from my point of view, and one of the reasons why I wrote this post in the first place, was having got those fundamentals down, when I came to look at the design patterns, I could see what the point of them was now. Whereas before I was kind of using them somewhat blindly. It's like, oh, someone said in this situation the factory pattern works well, or you can see how much I use them. There's another one I really do like, I forget what it's called. Suddenly you can look at it in terms of the solid principles. It's, okay, because if we didn't use this pattern, we would break the single responsibility principle, or we would break the Liskov substitution principle. And it allows you to be a lot more critical about when to use them, when not to use them, and you're a lot less likely to end up with a DAC controller master factory crazy object that doesn't mean anything anymore. So that's all I had. I appreciate it's a really big topic, and I've kind of tried to give a little bit technical, not too much. Are there any questions? Anything you'd like me to dive into more? Yep. Yeah.
Do you use OOP all the time then in your LabVIEW program now?
Yes, so that's my main way of organising my code. So it's not that, and this one caveats it, when I say I use OOP, it's not that I have like design patterns everywhere and all fancy names. It's just my main way of going. The same way someone might use action engines or functional global variables, I use objects in their place. Any other questions? Perfect. Well, I'm going to be around all day, so do let me know if you want to dive into anything more.
Also,
Right then, I think in the agenda we're up for a 15-minute break, so grab a drink, nip to the toilet, do whatever, and we'll start back again in about 15 minutes.
Yeah,